Hey, welcome back. In the last video, we initialized our neural model to have two input nodes in the input layer and a single output node with a sigmoid activation function. We plotted our linear model given the random parameters that were assigned to it and concluded that it does not fit our data well. We need to train this model to have the optimal weight and bias parameters and fit this data. The criterion by which we will compute the error of our model is recall cross entropy. As we are dealing with only two classes, our loss function will be measured based on the binary cross entropy loss, BCE loss, and this loss function is accessed from the NN module. The next step, as we did in the last section, was to specify the optimizer that we will use to update our parameters. The optimizer will use a gradient descent algorithm, notably stochastic gradient descent, an optimization algorithm that we can access from torch.optim.sgd as in stochastic gradient descent. And just for review, let's recall the sequence of events where first we compute the error of our model based on the cross entropy criterion, and then having computed the error, we take its gradient, its derivative, and by subtracting the derivative from the parameter values, the weight and the bias, it updates them in the direction of the least error, descending with the gradient. So inside of our stochastic gradient descent function, we pass in the model.parameters, the parameters that we wish to update at every iteration. And for the second argument, we specify the learning rates. And recall that when subtracting the gradient from the parameters, to update the parameters, you must multiply the gradient by a very small number, the learning rate, and the learning rate simply corresponds to the tiny steps that we take to reduce the error in every iteration. These tiny steps need to be sufficiently small, and we will use a reasonable initial learning rate of 0.01. Now that we've specified the configurations for our training process, it is actually time to train our model. We will train our model for a specified number of epochs. An epoch simply representing a single pass throughout the entire data set, and we iterate throughout this entire data set, calculate the error function, backpropagate the gradient of the error to update the weights and biases, and as you may already know, there is no concrete answer as to how many epochs one should run, as gradient descent is an iterative process. We need to pass in the full data set through our model multiple times to ensure optimal results. If you don't specify enough epochs, the model will underfit. And in the case of this very simple data set, I'm not too worried about overfitting issues, so we will just specify 1,000 epochs for the training process. I found that to provide enough iterations for the model to properly train. And now for every epoch iteration, for I in range epochs, given that for every epoch we want to minimize the error of our model, such that the error is simply a comparison between the predictions made by the model and the actual labels, we will first grab the predictions with ypred is equal to model.forward x. Simply enough, from our training data x, for every point within x, we take its x1 and x2 values, and we use our current model to make predictions using the forward method, all of which is then stored inside of ypred. Then we compute the loss, which is calculated based on the comparison between the predicted values made by the model for each point ypred with respect to the actual labels of each point y, ultimately to compute the error function with respect to the predicted values and the actual labels. We set our loss equal to the binary cross entropy criterion, and we will calculate the binary cross entropy for both predicted values in comparison to the actual labels. And for every epoch that we iterate through, we will print the epoch I that's currently being iterated through, as well as the loss associated with it, the loss.item. All right. And in order to visualize the decrease in loss at every single epoch, recall that typically what we do before the for loop is we set losses equal to an empty list, and for every loss that we compute, we will append it into our losses list losses.append loss.item. Notice how similar this is to how we did linear regression. The process really doesn't change when training neural models. Whether you're classifying data into discrete classes or fitting a model into a continuous set of data points, it doesn't really matter. The training process is relatively the same, aside from a few configuration differences that we had to place in accordance to our perceptron-based model. And so we will use this list to graph our losses at every epoch and see the improvements in our model. And having computed the loss at every epoch, we must minimize that loss. Recall that in gradient descent, we take the gradient of the loss function, the derivative. To compute that, we use the dot backward method, loss.backward. And having computed the gradient, we update our model parameters with optimizer.step using the optimizer that we initialized earlier. And as I've already mentioned before, all optimizers implement the step method that's used to update the parameters and can be called once gradients are computed with the dot backward function, as was just done. We are almost done implementing the training process of our model. And before the optimization step, recall, before computing any gradient, we must first set the gradients to 0, since gradients accumulate following the loss.backward call. We will need it to start from 0 to ensure accurate results. And we do this with optimizer. Let me just do it after loss.append. We do it with optimizer.0 grad. So, as you may have already guessed, every model we train in the PyTorch course going forward will follow this very same process, so we won't always have to code it from scratch. Since we begin by making predictions using our model, compare the predictions made by the linear model to the actual labels that belong to the points, whether it's 0 or 1, and based on the determined loss, the binary cross entropy, we then use an optimization algorithm, in our case stochastic gradient descent, to update the weights of our model in the direction of the least error, thereby minimizing the error function of our model, and we attempt to minimize the loss iteratively to obtain a model with optimal parameters, the model that best fits our data. And running this cell, we get an error, and I fell for the trap that I warned you about, and that is, this is an array. We initially converted them to tensors for this very reason. So let's go back and put this as x data and this as y data and try this again. And our model seems to be trained, but we get a deprecation error, being that in the way we configured the loss criterion, it is expecting a two-dimensional shape of 101 for both the predictions and the labels. The labels, which we initialized, does not follow that format. If you were to print it, you'd realize that. So what we do is we reshape it to have two dimensions, 100 rows and one column. Let's run this. And what we're going to do is actually reset the runtime and then rerun all of our cells. I will see you on the other side. All right, and we're back. Notice as the epochs progress, the error, the loss, starts to get significantly smaller, eventually converging to a reasonable value of about 0.25. For the purposes of this tutorial, this is quite reasonable. You once again have trained a model using gradient descent to fit a set of data points, classifying these data points. And to better visualize this process, let us now plot the loss on a graph. On a new cell, we run plt.plot. The x-axis will be the number of epochs, range epochs. The y-axis will be the losses. We now call plt.ylabel. We will name the y-axis loss, plt.xlabel. We will name the x-axis epoch. And running this cell, it seems that our model still has more room to converge. The loss hasn't been fully minimized within 1000 epochs, although one would consider fine-tuning the hyperparameters to ensure a more efficient training process. This is something that will be covered later on throughout the course, but for the purposes of this tutorial, the error is reasonably low, confirming that 1000 epochs is an appropriate amount of iterations to train our model. Which begs the question, visually, how well does our new model fit the training data? To visualize how well the model fits our data set, we can plot our new linear model by simply calling plot fit trained model. Plotting this data, we see our training data and we see our linear model, which has been trained to fit our training data. And it seems like it fits our data really well. Using previously labeled training data, we trained a model to have the optimal parameters in classifying this data. And now using this model, we can make accurate predictions on newly inputted data which don't have a label. We will do that in the next lesson.